This explainer. Today we're putting on our detective hats to solve a genuinely fascinating physics mystery. Sometimes physical phenomena just seem to magically align mathematically. But we have to ask, is it magic or is it a fundamental truth of the universe? Well, that's exactly what we're here to uncover by looking closely at motional electromotive force, or EMF. Get ready, because we're going to break down some pretty complex ideas step by step to make absolutely sure we grasp the mechanics at play here.
So let's dive right in. We've got two absolute heavy hitters in physics: the Lorentz force law, which tells us how individual charges behave inside magnetic fields, and Faraday's law of induction, which shows us how changing magnetic environments induce an EMF. And the profound question we're tackling today is this: are these two fundamental laws just happily aligning in some mathematical coincidence? Or is there a deeper underlying connection? Like, should Faraday's law be treated as a general rule that works for moving wires, or is it strictly for stationary loops? Let's follow the evidence.
Picture this: a wire loop moving through a magnetic field with a certain velocity. As the line element sweeps out an area, it actively changes the total magnetic flux passing through that loop. Now, according to our macroscopic physical laws, this change in flux generates an EMF. But we want to zoom in closer than that. We want to know what is actually happening to the individual charges inside that wire as it moves.
To crack this case, our very first clue is isolating a specific variable, F0. Think of this as our microscopic magnifying glass. Basically, F0 represents the Lorentz force per unit charge acting on the free charges within our moving conductor. By zooming in on the force applied to just a single unit of charge, we can build a pure force field equation. That tells us exactly how those moving charges are getting pushed around by the magnetic field, completely independent of how much total charge is actually in the wire.
Okay, to prove this connection, we're going to construct a logical framework in 3 bite-sized steps so we don't get bogged down. First, we'll define exactly what EMF is in terms of the total work done. Second, we'll establish our Lorentz connection by looking at the specific forces at play. And third, we'll integrate this force around our closed loop to see if our microscopic view actually matches our macroscopic law.
Right, step 1. By strict physical definition, the EMF around a closed circuit loop is the total work done by non-electrostatic forces per unit charge. Imagine a single test charge. The EMF is the amount of work done on that exact charge as it travels once completely around the loop. It's completing one full lap around the circuit. This physical definition, this idea of one full lap, is the absolute foundation for our entire proof.
Step 2 brings us to the Lorentz force connection. When a conductor moves through a magnetic field with a specific velocity, a force acts on the charges inside. The total Lorentz force is the charge multiplied by the electric field plus the cross product of velocity and magnetic field. But remember our clue, F0? We divide out the total charge to get our pure force per unit charge. So F0 simply equals the electric field E plus the cross product of velocity V and magnetic field B. In a case of pure motional EMF, where there's no time-varying magnetic field creating an induced electric field, this boils right down to just that V cross B component. And here's where the magic happens in step 3. To find the total motional EMF, we take the line integral of this pure force per unit charge along our closed path. Because of some vector identities relating to the swept area, something absolutely beautiful happens. When we integrate this pure magnetic force around the loop, the math just elegantly collapses. The line integral of the Lorentz force perfectly equates to the negative rate of change of magnetic flux. Our microscopic force literally, mathematically derives macroscopic Faraday's law. How cool is that?
Now, for the ultimate test. Think of this as our scientific boss battle. It's one thing to prove this with a simple moving wire loop, but what about a really complex scenario? Imagine a solid metal disk of radius r, lying flat in the xy plane, and it's rotating with an angular velocity omega about the z-axis. It's sitting right in a uniform magnetic field pointing along that same z-axis. And the circuit is completed by connecting a resistance from the axis to the outer edge through sliding contacts.
So, why is this a boss battle? Well, calculating standard magnetic flux through a fixed circuit for a spinning disk gets incredibly tricky, and the reason is that the current isn't neatly flowing along a simple defined closed wire loop anymore. The disk is a solid sheet of metal. The current just spreads out everywhere. So trying to use the standard rate of change of magnetic flux on a fixed imaginary boundary in the disk actually fails to give the correct EMF. This is because the line integral of the Lorentz force is independent of the exact path in the disk.
Because of this massive complexity, we're going to put our two distinct mathematical paths side by side to see if they truly converge on the same answer for this rotating setup. First, we'll calculate the EMF directly using that Lorentz line integral we just talked about. Then we'll use a clever little workaround to calculate it via the rate of change of magnetic flux. If these two totally different methods give us the exact same result, we know for sure the connection is absolute.
What's really remarkable here is how clean path 1 actually is. We calculate the velocity of a point on the disk as angular velocity omega times radius r. The Lorentz force per unit charge is the cross product of that velocity and the magnetic field B, giving us omega times r times b. To find the total EMF, we just integrate this force from the center of the disk out to its edge r. The integral of r dr is 1/2 r squared, so we arrive at a perfectly clean equation. EMF equals 1/2 omega r squared b.
Let's tackle path 2. Since standard fixed circuits fail us here, we can imagine a straight wire extending from the center to a point on the edge. As the disk rotates, this imaginary wire sweeps out an area, and this swept area increases the magnetic flux. When we calculate the exact rate of change of this specifically defined magnetic flux over time, all those complex terms beautifully reduce down, and it yields the exact same formula, 1/2 omega r squared b. Both paths reach the exact same mathematical conclusion.
So, returning to our initial mystery, is it just a coincidence? No way. Absolutely not. Even in the most general situation, the motional EMF generated in a moving wire loop by the Lorentz force is the exact same as that computed from the rate of change of magnetic flux through the moving wire. We've elegantly proven that Faraday's law of induction and the Lorentz force are deeply, fundamentally intertwined. It's a stunning display of how microscopic behavior directly writes the macroscopic rules of the universe. And honestly, this isn't just theory. It's the fundamental truth that makes all our electric generators and motors possible.
But before we wrap up this explainer, I've got a fascinating puzzle for you to chew on. We've proven all of this for conductors, right? Where charges are totally free to move. But what happens if you replace that metal loop with a non-conducting material? If a non-conductor moves through a magnetic field, does that sweeping area still generate a motional EMF, even if the charges can't easily flow to create a current? I highly encourage you to think about how the Lorentz force applies to those bound charges. Thank you so much for joining me on this deep dive, and keep questioning the physical world around you.